Naming ionic compounds. This might repeat a little bit what we did on Tuesday, but that's okay. First step to naming an ionic compound is identifying that it is one. Okay, we identify ionic compounds because they're going to contain a metal. And they're going to have one or two other nonmetals in them. So if you look at the formula for the compound and the first element is a metal, bang, you can assume it's ionic. There is one exception that we will run into, an ionic compound that doesn't start with a metal, and that is a compound containing ammonium ion. So if you see something like ammonium hydroxide, that doesn't start with a metal, but it starts with this NH4 guy, and that is ionic. That's the only exception we're going to see. So there are two different types of ionic compounds based on what kind of metal is in it. The metal ions we've talked about so far have been in groups 1A, 2A, 3A, zinc, and silver, and those only form one charge. The other metals form more than one charge. Iron can be +2 or +3. We can't tell by looking at the periodic table, and so we have to treat those guys a little differently. We're going to talk about these guys first. So what your book calls type 1 is those ionic compounds where the metal forms one ion. These are groups 1A, 2A, 3A, and then zinc and silver. And I'm going to repeat that so many times during lab today that you should be able to chant that before you leave. Groups 1A, 2A, 3A, zinc, and silver. That's a group of metals that we need to remember. Those guys are easy because they always have the same charges. Groups 1A, 2A, and 3A, their charge is just their group number, +1, +2, or +3. Metals always form cations. Yes?
Close it down a little bit?
Yes, absolutely. Those guys are loud, aren't they? You can close it all the way down if you want. Zinc and silver are always, zinc is +2 and zinc is +1. And I really need to put a periodic table in here, but I'll show you over here. So here's aluminum, right? Aluminum's in group 3A, +3 ion. And so then I imagine going down the stairs, zinc and silver, and you count 3, 2, 1. Actually, maybe I'll draw that in here. So poor YouTube people. Let's see. So there's boron, there's aluminum. So here is aluminum in group 3A. Here's zinc, and here's silver. This is +3, +2, +1. Stair steps down, okay? So you just have to remember that zinc is +2 and silver is +1. The other type of ionic compound your book calls type 2, those are ionic compounds that contain any other metal. Those can make different kinds of ions, and so we're going to end up using Roman numerals for those guys. So here's a list from your book of the metals that only form one ion. And so we've got the group 1A, 2A, 3A, zinc, and silver. There are possibly some exceptions to this. I'll tell you right now, we do lie to you a little bit in Chem 20. But it's like lying to a child for their own protection, right? If we told you everything, you'd just be completely overwhelmed. And so we're just going to start with the basics. You might ask, well, what about the other elements in group 3A? What about gallium and indium? Well, those are most likely going to form a +3 ion also, but we're just not going to run into them in this class, okay? These are some of the metals that form more than one ion. So here's chromium. It's a metal. Find it on the periodic table, Cr. Is it in group 1A, 2A, 3A, zinc, or silver? No. That means it can form more than one ion. Well, what ions does it form? We can't tell from the periodic table. So if we're going to give these ions a name, there happens to be chromium 2+ and chromium 3+, bless you. So we put the charge in Roman numerals after the element name. So this is chromium 2 and this is chromium 3. There's an older system, it's called the stock system, where they use suffixes us and ic. It's there, it exists, we're not going to use it. Okay, that's the old system, we're just going to learn the new one. But things like, your toothpaste has stannic fluoride in it. Well, stannic is the tin 4 ion. Did you know there was tin in your toothpaste? There is. Tin ion. So you may see these names, but I will not require you to use those on an exam. And then your book talks about binary ionic compounds. So these are 2 different elements. Binary means 2, right? So that means 2, not 1, not 3, 2, exactly 2. So we've got 2 different elements. We're going to have a metal, and so we'll give the name of the metal ion, and then we'll leave a little space. And then we take the nonmetal, we change the ending of its name to "ide." So I think of the metals as being masculine and the nonmetals as being feminine. When you address a formal invitation, it's Mr. and Mrs. Tom Smith, right? You don't do it Mrs. and Mr. Would we understand what you meant if you did Mrs. and Mr.? Sure, we'd understand, but we'd say that's not quite right. Why do we do it that way? Why do we do Mr. and Mrs.? Because that's the way we always do it. You could go off and say, well, they're, sexist things, and oppression by males and stuff. No, we just always did it that way. So take the same attitude with this. Why? Just because we decided to do it that way. The metal first, and then the nonmetal. Now, traditionally, when a woman marries, she changes her last name, right? So the nonmetal in my fantasy world called Chemistry Land, the nonmetal is feminine. And when she becomes part of a compound, she changes the ending of her name. Okay? The metal doesn't do that. Yeah. So let's look at this example. So NaCl. Now we're talking about ionic compounds, so we know that this is ionic. But if we didn't know, we would identify it by looking at the first element, Na, sodium. We're going to find it on the periodic table. It's on the metal side. Because it's a metal, we know this is an ionic compound. So we have to find the name for this ion. We find it, we already found it. It's in group 1A. So it's in group 1A, 2A, 3A, zinc or silver. Told you I was going to say that a lot. So it's just sodium ion. And then the nonmetal is chlorine, and so she's going to change the ending of her name. She's going to change her name from chlorine to chloride. And then we just write them next to each other. Sodium first, the guy first, and then the girl. Sodium chloride. Any questions? These are some of the common monatomic anions. Monatomic meaning it's just one atom. So fluorine, when it becomes an ion in a compound, fluoride. Chlorine becomes chloride, bromide, iodide. So these guys, the halogens, you lose the ene and put in ide. Oxygen, we're changing the ending. It's not always just the last syllable. Here, we're not just getting rid of the en, we're getting rid of the last 4 letters. So oxygen becomes oxide. Now, if you wrote oxygide, I might chuckle to myself, but I wouldn't mark it wrong on this worksheet. I'd just fix it for you, right? Just kind of takes a little while to get used to what these things are. Sulfur becomes sulfide, nitrogen becomes nitrite. So all the nonmetals do that. When they form an ion by themselves, you change the ending of their name to ide. So let's do a couple examples. Let's name this guy. KBr. Potassium bromide. So the first element is potassium, so we just write his name. And the second element is bromine, and she changes the ending of her name to bromide. Potassium bromide. Because potassium is in group 1A, we don't need anything else. He always forms a +1 ion. How about this guy? Zn3N2. Zinc nitrite. You guys are much more responsive than the Tuesday group. It's really encouraging because apparently the exam did not fry your brains. That's good. So zinc. Group 1A, 2A, 3A, zinc or silver. Just the element name. And then this is nitrogen becomes nitride.
So the 3 doesn't have anything to do with the name?
We don't need to do anything with the 3 or the 2 because from the periodic table we know what the charges are. I don't really have this in the PowerPoint slides, and I should, so I'll just do it right now. If we're writing a formula from the name, what do? Well, zinc, we need the formula for the zinc ion. Well, the symbol is zinc, and then we look at the periodic table, and it's not in group 1A, 2A, 3A, but it's zinc. And that's one of the ones that we can tell, and so we go from aluminum +3 down one step to zinc. Zinc is +2. Nitride, we find nitrogen on the periodic table. We're counting -3 from the noble gases, so this is N3-. So we don't need any information in the name to tell us about the relative numbers, because now we have those charges. When we do that crisscross thing, we end up with Zn3N2. Okay. A lot of times students want to, do something like try zinc dinitride or something. It's not necessary. There's another group of compounds where we do have to do that. But all of these names are designed to be as concise as possible while conveying all the needed information. Type 2 binary compounds. So these are the metals that are not in groups 1A, 2A, 3A, zinc, or silver. We don't know what the charge is from the periodic table, so we have to tell each other. And we use Roman numerals to tell each other. So just a quick review of Roman numerals. 1 is 1 capital I. 2 is 2 capital I's. 3 is 3 capital I's. Now, if they just went on like this, essentially they're just drawing lines, right? And that would get really tedious if you had to, write 527. 527 lines. So they started using other things. One of these days I'm going to look up the history of Roman numerals. So this is 5, and then 4 is 1 before 5. And 6 is 1 after 5. Okay, and I don't think we're going to go any past 6, but if you needed to, 7 is 2 after 5. Okay? So those are the Roman numerals. So copper is one of those elements that's not in group 1A, 2A, 3A, zinc, or silver. So there's 2 ions, there's Cu plus and Cu2 plus. So the name for the Cu plus ion is copper with the Roman numeral 1 in parentheses. There's no space between copper and the parentheses. It's like part of its name. This is a little bit like, Henry VIII and Henry VII, where men use Roman numerals behind their name when it's a family name that's passed down from generation to generation, so that you can tell which Henry are you talking about. So copper 1 and copper 2. It tells the charge, not how many of them there are in the formula. That's a common misconception. It's the charge on the ion. So these compounds follow this pattern here. You've got the name of the cation with its charge in Roman numerals, followed by the base name of the anion with its ending changed to "ide." Well, when we're naming these, we're going to have to figure out what the charge is. It's not specified in the formula, but we have to specify it in the name. And we do that by looking at the chemical formula, and we look at the charge on the anion. And we remember that the charges have to add up to 0. So if we're looking at FeCl3, Fe, and there's 3 chlorines in there, right? That's what FeCl3 means. We know the charge on chloride by looking at the periodic table. It's a -1 charge. There are 3 of them, and so the total negative charge is -3. Does that make sense? In the formula, we know there's only 1 iron atom. The total positive charge has to equal the total negative charge, but opposite in sign. So we know that there's a total +3 charge, and iron is the only one there, and so he must be +3. And so this is then going to have the name iron 3 chloride. Some of you have developed a math phobia or other issues with math, whatever you want to call them, and you feel like you can't do math. This type of math is confusing to a lot of my students because we're talking about these weird things, electrons and charges and chloride ions and stuff. But if I talk to you in terms of moms and little boys and cookies, you can do this math without even really thinking about it. So these are the women, these are the moms, and the number of negative signs is how many cookies they're bringing. So she's bringing 1 cookie, and she's bringing 1 cookie, and she's bringing 1 cookie. How many cookies do we have? We have 3 cookies. Each of these is a little boy. There's only 1 little boy. We take the cookies, 3 cookies, and we distribute them among however many boys there are. There's only 1 boy. How many cookies does he get? He gets all 3 of them. That's the extent of the math involved in this. Okay? We can all do that. Any questions? Oh, I already did that. Let's do a couple of examples here. So name the compound PbO. And sometimes, people get smart and say, I think we should call him Steve. No, we're going to give him his real name. Well, Pb is what? Lead. Is lead in group 1A, 2A, 3A zinc or silver? No, it's not. That tells us this needs a Roman numeral. So let's save a space. We'll put the parentheses in there to remind ourselves to come back and fill that in. And then O is oxygen. We change her name to oxide. So this is lead something oxide. Now we have to figure out the charge. So here's lead, we don't know what the charge is, and here's oxygen. As an ion, excuse me, what charge does oxygen have? 2 negative. The formula shows us that there's 1 of each. So the charge on the lead must be +2. So then in Roman numerals here, we write 2. So that's lead 2 oxide. About Cu2S. Cu is what element? Copper. Is copper in groups 1A, 2A, 3A, zinc, or silver? No. Therefore, it needs a Roman numeral. Leave a space. S is sulfur, which becomes sulfide. So this is copper something sulfide. Okay, I'm getting several people saying it's copper 2 sulfide. It's copper 1 sulfide. It's so tempting to say copper 2 because there's a 2 just staring you in the face. It's not the number of atoms or ions, it's the charge. So let's think about this. We've got Cu, we've got Cu, and we've got sulfur. Sulfur has a charge of what? 2 minus. 2 minus. And so then we must have +2. So there's 1 mom bringing 2 cookies. There's 2 little boys. How many cookies do they each get? 1. Which two are you asking about? The charge?
Yeah, like how do you know it's like a Roman numeral 2?
Oh, up here?
No.
Well, down here it's not a Roman numeral 2. We're getting to it. So we're looking at this right now. So we figured out that the charge on each of these was +1 because there were 2 of those to 1 of these. This had a -2 charge. You okay with that? So we figured out that these are +1. That is the Roman numeral 1.
There's a question of how do you know that sulfur's?
How do you know that sulfur's 2-?
Yeah.
That's an excellent question. So we look at the periodic table, and we're going to count backwards from the noble gases. These don't form ions, they're 0, no charge. Over here is -1. The next column where sulfur is -2. The next one is -3. We'll learn later why they do that. For now, just count backwards from the noble gases. You okay now?
Yeah.
Okay. Because if one person asks a question, usually there's like 5 or 6 other students that had exactly the same question, but they weren't brave enough to ask. Anybody else have any questions? Yes?
So it's 0, then -1, -2.
-3.
Is it just to 3?
It just goes to 3.
Okay.
Yeah. And you'll never see an ionic compound in this class with carbon or silicon or anything like that. So we don't have to worry about it. Yeah, and then the metals, anything to the metal side of that stair-step line, always a positive number, except for our little misbehaving child, hydrogen. Hydrogen makes a +1 ion, also makes a -1 ion. Just, he's the baby of the element family, and he gets away with breaking rules. Any other questions? So those were binary compounds, only 2 elements. There are also ionic compounds that have more than 2 elements in them. These have what are called polyatomic ions. The prefix poly means many. Atomic refers to atom. So these are ions with many atoms in them. You just have to memorize these guys. They have special names. They are related to the elements that are in the ions, but you just have to remember them. I mean, how do you learn the names of people that you encounter? You just memorize them, right? There's really no rhyme or reason to it. So sometimes we just have to memorize junk. So these are the ones that you should memorize. Bless you. Now, if we look for commonalities in here, we see that most of these have oxygen in them. Ammonium doesn't, cyanide doesn't, but pretty much everything else has oxygen in it. Ammonium is the only one that's a positive ion. All the rest are negative. And most of them end with either ate or ite. Hydroxide is a little different. That's a very important one. And cyanide ends in ide, and peroxide. But all the rest of them end in ate or ite. And you just have to memorize them. You memorize the name, the formula, and the charge. So 3x5 cards, flashcards, keep them in your pocket. You're stuck at a train or a red light, pull them out, go through them. That's the best way to learn them. So let's talk a little more about these guys. So the ones that have oxygen in them are called oxyanions. They're anions containing oxygen. And there are a series of them that are related. Let's go back here real quick. Here's nitrate and nitrite. Their names are very similar. Their formulas are very similar. Right? Here's hypochlorite, chlorite, chlorate, and perchlorate. All very similar. There is a pattern within those that have the same element here. So these are all chlorine with oxygen, and there's a pattern in their names, and I'll show you what that is. So what I recommend is that you memorize the one whose name ends in ate. So nitrate, you just memorize that one. But then the ite one is like Bud Light. What's the difference between Bud and Bud Light? Bud Light has a third fewer calories, right? Less filling. It's less, right? The ite is the light version of nitrate. It has one less oxygen. The charge is the same. The number of nitrogens is the same. The only difference is one fewer oxygen. Here's sulfate and sulfite. By changing the 8 to ite, the light version, we just reduce the number of oxygens by 1. So the light version has one less oxygen than your regular 8 version. Okay? So a lot of them, sulfate, phosphate, nitrate, there's only 2 in the series. But the halogens actually have 4 ions in their series. So here's chlorine. So here's chlorate. This is the one you would memorize, ClO3 minus. Chlorite is the light version, one less oxygen. ClO minus is one less oxygen than the light version. So we're going to put a prefix in front of chlorite, hypochlorite. Hypo means below or less than. Where does a hypodermic needle go? Below the skin, below the dermis, your skin, right? Hypo means less. So this is less than the light version. And then we have one that has more oxygen. If someone is hyper, do they have more or less energy? Hyperactive. More active or less active than regular people? More active. Per or hyper means more. So perchlorate has one more oxygen than the 8. You memorize this one, you remember this pattern, and now you can name and write formulas for 4 ions by memorizing 1. Over here, we have the series for bromine. Bromate has the same pattern as chlorate. All that's different is it's bromine instead of chlorine. Look on the periodic table. Chlorine and bromine are in the same group, the same column. Sometimes we call those chemical families. Children in the same family often have similar characteristics. If I showed you a picture of my children, you'd go, oh yeah. They look like they were made with a cookie cutter. And they share some common things. So far, I've got 5 sons, and so far, 4 of them play football. The 5th one would, but he's only 6, and they won't let him play yet. And the older 3 play guitar, and they all love to play video games and eat white rice, and they're surprisingly good at origami. And, you know, it's just some of these stereotypes of being half Japanese are really true, at least for my children. But they have these things in common. So bromine and chlorine are like sisters, and they're going to do the same thing when they get together with oxygen. So hypobromite has the same formula as hypochlorite. You just put Br in there instead of Cl. Iodine is also in that family, another halogen sister. So iodate, IO3 minus. Same pattern. You see that? Same pattern here. Iodite is one less oxygen. Hypoiodite is one fewer yet. And periodate is one more. So remembering the sisters and the pattern and this one, I should circle that, chlorate and its formula. There you've got 12 polyatomic ions and their names, because those are all very systematic. Here's a note for Mastering Chemistry. When it asks you to name these, it wants you to include the word ion. So if you're naming this guy ClO minus, you need to write perchlorate ion. On this worksheet, I don't care. Either way is fine. But Mastering Chemistry cares a great deal about that. Any questions? here's some examples of where these polyatomic ions are found in products that you might be familiar with. Sodium hypochlorite. Well, what's the formula for hypochlorite? It's ClO with a -1 charge. And then if that's paired with sodium, sodium's in group 1A, it has a +1 charge. So this must be NaClO, sodium hypochlorite. That's bleach. Household bleach is a solution of sodium hypochlorite. Sodium bicarbonate. Well, I kind of skipped over those. Let's go back and look at those real quick. I tend to forget about them. There's a couple of weirdos in here. Hydrogen carbonate. This is one of only a very few ions that has two names. Just like I have a friend whose name is Mary Ann, right? She uses her first name and her middle name. Most people just use their first name, but some people use a second middle name all the time. So this is like Mary Ann, hydrogen carbonate. An older name is bicarbonate. Personally, I prefer hydrogen carbonate because I think it's more descriptive and less confusing, but bicarbonate is also good. And then down here we've got hydrogen bisulfite. I'm sorry, hydrogen sulfite or bisulfite. You have to choose one of these. Don't say hydrogen bisulfite like I just did. And this is hydrogen sulfate, and then you also have hydrogen phosphate. For some reason, that's never called biphosphate, but sodium bicarbonate. That's baking soda. You mix that with something slightly acidic, and it generates carbon dioxide and makes your biscuits nice and fluffy. Calcium carbonate, present in antacids, neutralizes stomach acid, makes your heartburn a little better. Sodium nitrite, preservative in meats, especially things like hot dogs and lunch meats. So nitrites, are they good to eat? They good for you? No, a lot of people avoid them like the plague. They're not great for you, but look what they prevent. Botulism. I'd rather eat some nitrates than get botulism. So let's do some examples here. Let's look at this compound. Always look at the first element. Ask yourself, is that a metal? And you answer that by finding it on the periodic table. So Mn is right there in the middle. It's to the left of the line. It's a metal. Do you know what the name of it is? Manganese. Not magnesium. That's Mg. And don't put them together and call them manganesium. That's always fun. Manganese. Does manganese need a Roman numeral? Yes. It is not in groups 1A, 2A, 3A, zinc, or silver. Got that memorized yet? 1A, 2A, 3A, zinc, or silver. So I'm going to leave some space there. And then we're going to look at the rest of this. Sometimes students get a little creative. I'm all for creativity, but there's no room for creativity in nomenclature, which is one of the things I like about it. There is one right answer. There's one right name. Ionic compounds contain two different ions. Do not split them into 3 or more pieces. That doesn't happen in this class. So there's the metal and there's everything else. So this has one name. It's not nitrogen dioxide. It's nitrite. For today, you haven't memorized these. Look it up in the table. NO2 is nitrite. Remember, the parentheses are like the shrink wrap around a bundle pack of something you might purchase at the store. And the 2 on the outside tells us we have 2 of these units. They come together. If you buy a nitrogen, you're going to get 2 oxygens free. You can't say, no, I don't want the oxygens. And say, no, it's shrink wrapped together. You have to take them. Throw them away and you get outside, but you have to take them out of the store like that. Right? The NO2 always comes together. Don't cut it up when you try to name this. So that's nitrite. How do we figure out the charge? What Roman numeral to put in here? we look at the charge on the anion. So let's draw ourselves a little picture. At first, you might just need to draw pictures like this. In the table, look up the charge. It's -1. There are 2 of them. There's 2 of these guys. That gives us a total of -2. How many manganese ions are in this formula? Just 1. So there's one guy over here. We don't know what his charge is. That's what we're trying to figure out. If this side is -2, this side must be +2. There's only 1, and so he must be a 2+ ion. So then the number that goes here is 2, because that is the charge on this ion. The charge goes in there as a Roman numeral, not how many there are. Any questions? How about this one? That one looks like Cocoa 3 might be a good name for it, but that's not. What's the first element? CO. Cobalt. It looks like carbon and then an O, right? Pay very careful attention to the capital letters and the lowercase letters. And when you write these formulas on your paper, it matters whether you have a lowercase o or an uppercase O. So cobalt. Does cobalt need a Roman numeral? Yes. Not in groups 1A, 2A, 3A, zinc, or silver. And then what's the rest of this? Carbonate. The carbonate is also CO, but that's a capital O. Capital O is different than a lowercase o. Yes, it's very picky, but it's also very concise. And so once you get the hang of it, we can write it out very quickly. What's the charge on the cobalt ion? 2. How did we do that? It's magic. No, it isn't. We have 1 carbonate ion and 1 cobalt ion. We look up the charge on the carbonate, it's -2. It's just one of each here, so it's easier to think about. So this must be 2+. The charges on the ions have to add up to 0. And when we write the formulas for the ionic compounds, we never write the charges in there. It would get all cluttered and messy looking. It's complicated enough without that. Any questions? Yes? I got the -2 for the carbonate ion from this table. There are some patterns in the periodic table regarding those, but I don't find that most students find them all that useful. For this, rote memorization just seems to be the best. So we look it up in the table, here's carbonate, and we see that it has a -2 charge. Any other questions? That's a good question. Is the table going to be on the test, or do you have to memorize it? I'll get back to you on that. Get that.